Hi everybody, once again. In our last video, we learned about the existence of a quantity called resistance, which we defined as the ratio of voltage to current. In other words, the more resistance a circuit or a circuit element has, the less current goes through it. Well, where does resistance come from? In our last PhET simulation, we saw that there are these little black dots, and you'd be justified in saying well, resistance comes from the little black dots in the wire. Of course it isn't exactly though. The little black dots are really a representation of how hard it is for electrons to pass through a wire by representing how many collisions they're going to get into with the other material in a wire. The more collisions they get into, the less direct a path they're going to take, and the longer it's going to take them to get where they're going. In a lot of sources, you'll hear about or you'll read about an analogy of current as water running through a pipe, with the voltage being something like the water pressure, but the truth is that just isn't very accurate for circuits. In a pipe, the water needs to come from some source like a reservoir, and that leads lots of people to think that the battery in a circuit is like a reservoir of electrons, which then go racing around a wire. If you remember the simulation we did last time though, it made it pretty clear that the conducting path we used to create the circuit, the wire, had lots of free electrons already in there. So what we should think about instead for the battery is that it provides a sort of energy gradient that makes those electrons that are already there want to move around. A better analogy might be thinking about a marble track with a lot of marbles already in there. The battery is kind of like tilting the track up, and that tilt is what makes the marbles or the electrons roll in a certain direction. Back to the little black dots. We do have a way of predicting how much resistance a given wire is going to provide to a circuit, and one thing that matters is what the wire is made of. That's called the resistivity of the wire, or ρ, and as we said before, it's a sort of measure of how hard it is for the electrons to get through a particular material. So changing the resistivity changes the resistance. As you might also expect, I can increase the resistance of a wire by increasing the length of it, because a longer wire means a longer path for the electrons to travel, which means more collisions, which means more resistance overall. The last thing I can vary is the cross-sectional area of the wire, and as you would expect, a wider wire means there are more possible paths for the electrons to travel, so they can avoid collisions better and giving you an overall lower resistance, and vice versa. So now we can put all of these factors together into the equation. Resistance equals resistivity, which I write as a lowercase Greek r or rho. It looks like a p, but it's not a p, over area, and then use it, for example, in this. This is pretty much a straightforward plug and chug. We have the length right here. We can use the diameter to find the area, but the resistivity of copper, whoops, it looks like I forgot to say that it's copper, but the resistivity of copper, well, we're going to have to look it up. So get out your reference. Scrolling through the reference table, we're going to find on the electricity page that there's a little table at the bottom called resistivities at 20 degrees Celsius. And from that, we can immediately look up the one for copper, and we see the resistivity of copper is 1.72 times 10 to the negative 8 ohm meters. So we have all the pieces. What I'm going to ask you to do right now is pause the video and try and solve the problem yourself. Press play again when you're done, or you get. Okay, so let's solve the problem. Resistance is resistivity times length over area. We can immediately plug in the resistivity, 1.72 times 10 to the negative 8 ohm meters, and multiply by the length, which is 25 meters, and then divide by the area. Oops, what is the area? Well, we have to think of a wire as sort of like a cylinder. So the cross-sectional area of the wire is just going to be a circle, and the area of a circle we all know is pi r squared. So I didn't quite give you the radius, so I gave you the diameter, which was 4 millimeters, so the radius is going to be half of that. So I know in that case that my area is going to be pi times 4 millimeters over 2 squared. Change my 4 millimeters to meters by writing as 4.00 times 10 to the negative 3 meters over 2. square the whole thing, and that goes in this formula up here as well. And then put it all in your calculator, hit enter, and you'll find that the resistance of this wire, your final answer, should be 0.034 ohms, where the units really cancel out beautifully in the last step because I have ohm meters times meters, so that's meters squared divided by meters squared in the denominator. You might think that this is a pretty low resistance, and it is, but that's the point of using copper or another metal in the circuit. You want the wires to have a very low resistance, so you can pretend that the resistance is almost zero. One thing that you might have noticed on the reference table is that the resistivities are all given at a certain temperature. That implies that as the temperature changes, we can expect the resistivity to change. Thinking about those little black dots again, the simulation won't really let me show this, but all these little black dots are sort of jiggling around. I mean, you know that from chemistry, that molecules in material are moving around due to their kinetic energy. So as the temperature in the wire increases, the jiggling is going to get bigger, so to speak. That was an unexpected zoom. So these things are going to be moving around more and more. And the more they move around, the more collisions are going to happen, and the greater the resistivity, and the greater the resistance. Think about it as trying to run through a hallway when a lot of people are running around back and forth. You're going to run into more of them. So ultimately, we can conclude that as the temperature increases, that means the resistivity of the material is going to increase, and that of course means the resistance is going to increase. That doesn't matter for 99% of the problems we do. The only time it really matters is when you're dealing with a light bulb or something, because of course when a light bulb is on for a while, it heats up, so the resistance is going to increase, and that means the current over a long time is going to decrease. Okay, that's the end of our lesson about calculating the resistance in a wire. There are two exercises I'm going to need you to complete. One is going to be on the test wizard, which you guys all should have signed up for earlier this week, and the other is going to be just a file that I'm going to put up here. I'm going to need you to write your answers in your own handwriting, scan it, and upload it. Both of these are due by the end of Wednesday. To answer any questions, basically any time during the school day from 8 a.m. to 3 p.m., or you can email me or post comments below. I will see you guys next time for our next production of Pandemic Physics.